Everybody. Today we shall discuss about line coding or baseband shaping. So this step is required to combat the dispersion or band limitation posed by the physical signal transmission, that is the physical channel. All physical channel has some kind of dispersions, be it electrical or optical or any others.
So,
Yes.
when is the test? Like, so I was not well, so I did not attend the past one class, two classes. So,
Yeah, test initially I told that Friday, but this Friday I'm not taking the test. Or maybe I shall try Monday, but I will announce tomorrow if it is Monday. Okay.
okay. So, like, it is not.
Otherwise, it may so happen that I may take the test after the that mid examination. That is, we have a scheduled test between 21st to 20 that week, 21st week. So maybe we will take the first test there itself, and then we will take two more tests afterwards. That is also possible because right now our coverage is not that much. So maybe I will continue little bit before taking the test.
So that means tomorrow is no test, right?
No, no, no. Tomorrow, how can it be? I would announce at least few days before. But I have already told that there would be some test. So I think I will announce at least 2-3 days before.
Okay, sir.
So this is line coding or baseband shaping. Means we are in the physical domain, but not in the power domain. Transmission, truly transmission has not happened, but this could be done in the digital domain itself, or maybe in the analog front end. So both are possible. This is mainly to combat the dispersion and band limitation posed by the physical channel. So basically, this cause intersymbol interference. Or maybe we should write which causes intersymbol. So that means when we transmit two symbols, if there are interference between the symbols, so the chances of error will be more. So there are two aspects of that. One is that the channel could be noisy, and also the bandwidth can be very limited. Or maybe our signal transmission choice, signaling choice is such that it requires more bandwidth corresponding to per bit. Per bit it require more bandwidth. So if we choose that proper signaling method, so then probably it could be reduced to some extent. This aspect is also taken care in the power signaling, that is when we do modulation in the analog front end. There also to some extent it is taken care of. But here we will discuss the digital uh, coding of the digital coding, which is also known as the baseband shaping. The other aspect of the analog front end is the carrier band shaping. So
Why
there are several
that inter-symbol interference will happen?
which causes means this physical channel causes intersymbol interference. This dispersion and band limit posed, these two factors cause intersymbol interference. So maybe to reduce intersymbol interference.
So when we say baseband shaping, what do we mean actually?
So baseband means whatever frequency we are generating by the data itself, that is the bit. So this, like this 101 we are transmitting, okay. Suppose for a signal like this one is 00101 like this. So this is in the baseband. Now in the carrier band, of course, this may not be correspond to any voltage or etc. or may not be this kind of shape is available. So there actually it could be frequency modulated, phase modulated, etc. So therefore that signal characteristics will be changed. So in other words, if we take the spectrum, we shall discuss about the spectrum. If we take the spectrum, this spectrum is combination of this bit pattern and the basic pulse itself. So if a spectrum of a single pulse like this would be like that sinc function. Okay, so this is the frequency. This would be the spectrum. Now this spectrum, of course, is not limited, is not band limited. It goes to minus infinity and plus infinity because to keep the ideal square wave. So the moment we limit it, actually it will no longer be a square wave. So it will change the shape. Similarly, there could be dispersion. So that means we are transporting, we are launching energy of a channel at one end. Okay. So here we are giving like this, but it means basically the voltage level is rising if in terms of voltage, if we see say from 0 to plus V. So this may not become instantaneous. In case of optical, it could be say 0 to some intensity. Okay. Nowadays, most of the transmission is optical domain. However, in that case also, when we receive on the other end, okay, so the energy that is being received at certain moment will not be the full energy corresponding to this level L. This is suppose a level L. So this side actually we will receive first a part of that energy. So and then subsequently it will rise. It may happen like this in extreme cases. So most of the cases it will be little better than this, of course. It could be like this. So that means the rise font may change. So this is due to several factors. One of them is dispersion, which may occur due to several aspects of the physical channel. For electrical channel, it is like resistance, capacitance, inductance is there. It will act as a low pass filter. For optical channel, of course, it will go like, you know, that optical fiber carries like in zigzag path, and some part of the beam will go like this, some part of beam will go like. So part of the energy is transported through a path which is a little lesser than the other path, other energy path. So therefore the full energy is not received at a certain instant. So that is known as the geometric dispersion. There could be dispersion due to, because it's a material, so material always has some defects, and all those defects will have some scattering, so that there could be material dispersion. So overall there could be some dispersion causing like this. So therefore all these two aspects will cause that there would be this basic shape may not be intact at the receiving end. So there are several means to reduce this one, the effect, such that the detection of these two states, 0 and 1, becomes easier. So in effect, this is dispersion, and this is suppose band limit. Typical channel will have a band, band limit. In effect, this step is this step is required. To facilitate clear identification of zero state and one state. Of the digital data. So the first one could be a simplest would be the unipolar or bipolar. Line coding is unipolar. Or on-off. This is also known as on-off, where one is represented by transmitting a pulse, and zero is represented by the absence of a pulse. So this is the simplest one. It could be bipolar in case of polar. For polar signaling, 0 and 1 are represented by two distinct levels. And for bipolar, positive and negative pulses are used alternately. For representing 1. And no pulse for 0. So for bipolar, this is done, that is alteration of positive and negative pulses to combat the successive occurrence of 1. So if there are successive occurrence of 1, then there could be some residual level shift. So to combat that, actually it is switched between positive and negative pulses corresponding to the transitions from one bit to another bit. In some signaling formats, this is also done to enable clock sensing, because ultimately the digital data that could be read correctly based on the clock. Of course, nowadays all those informations are coded in the header, and accordingly the clock can be set. Earlier days, there so much was not there. So there used to be a clock sensing mechanism at the other end. And if there is no transition between the levels, clock sensing becomes very difficult. So that is, if there are too many successive ones or too many successive zeros, then the time may not be synchronized properly due to irregular clock sensing. So for that, to combat that, bipolar signaling was used. Of course, spectrum-wise also it has some advantage that we shall see. Now, again,
Sir, for bipolar signaling, it might happen that we have a positive pulse for 1 second and then 3 or 4 seconds of zero pulse, and then again a negative pulse. So, like something how that is synchronized with the clock signal.
yeah. So in that case, actually, this will be clock sensing will be done periodically when ones will be come. Then only clock sensing will be possible. Okay. Because actually clock need to be synchronized periodically, time to time. So at least for the one we can sense it, because if there is consecutive zeros, of course it is some difficulty. So to combat that, a second type of signaling came into picture. Again, to mark the transitions for both zero and one, a signaling method called return zero. Return to zero came into picture. So here what happens, the zero ones are transmitted at certain rate. However, the background clock is running twice the rate. So why it is so? Because in this case, we have to make an event at the middle of either 0 and 1 such that the level is shifted to the 0 level. So that can be done if the clock is run twice the rate. Advantage is that every pulse, every bit will have a synchronizing mechanism, and also the bandwidth, the DC bandwidth is shifted. So these are the two advantages. However, disadvantage is that we have to have a higher clock rate. So this is like if we plot this, the other, of course, known as non-return zero. So NRZ are simple in managing because it require, this is NRZ unipolar. So we have a plus B here, and then corresponding to 0 and 1, we have shifting of levels. So this is the simplest one. Now, disadvantage is that it has a DC bandwidth. And DC bandwidth in case of electrical channel had earlier a lot of problem too, because there would be some DC shift of the power or the voltage, so which used to cause a lot of problem due to common mode voltage generated by the circuit. So therefore, this was not this was modified by polar NRZ. So polar NRZ is basically the voltage is switched between plus B and minus B. So this is 0, 1, 0, 1, 1, 0. So in case this is non-return zero. If we have return zero polar, in that case we have here minus b, here plus b. However, in this case, we have an intermediate state. So this is minus b, it goes to 0, it switches to plus b. At the middle, it goes to 0. Again, it is minus b. Switch to 0. So this is like 0. This is 1, 0, 1, 1, 0. So in case of bipolar, of course, like for example, inner-jet bipolar, so for the 0, of course, we don't have. For the 1, we have here. Oh, no, sorry. Alternate pulses per 1. This is 1, only 1 is there. Then we have 0, 1. But suppose we have another one here. So 1, 1, 1. So like that. So this is an example of non-return zero bipolar. In case of return zero bipolar, it would be modified according to this. So there is another kind was popular, that is called the Manchester biphase format. Known as Manchester coding. So here one is represented by transmitting positive pulse. For 1/2 of the symbol. Again, here also we have to run the clock at twice the rate, data rate, to mark that half width for 1/2 of the symbol duration. Followed by a negative pulse. For the remaining half. Remaining half duration. And 0 is represented by reverse order pulses. So it would be, again we have plus B minus B. Say we have starting with say 0. So this is 0. Then this is 1. And then suppose we have another one. And okay, so this I have returned. So this is 0. So this is Manchester biphase coding. So there are many more are there. However, these are some of the prominent ones. But the purpose of our discussion is that for these line coding schemes, we will estimate the power spectra of the signal. Now we will try to estimate the power spectra. So these are also known as discrete pulse amplitude modulation. So now let us see how we can compute the power spectra, because our interest is that how the bandwidth requirement corresponding to various pulse amplitude modulation schemes. Intuitively, we can see that, like say for Manchester coding, we have avoided the DC bandwidth because of the polar biphase signaling. Similarly, for this one also we have non-retangent bipolar also we have avoided. Return zero polar also we have avoided the DC bandwidth. Non-return zero polar also DC bandwidth have been avoided, but unipolar of course we have a DC bandwidth. Bipolar also have a, of course, a component is there, DC bandwidth component will come. It may be, yes, it will come. So now to estimate the power spectra, so there are two aspects, because we have the symbols. There would be some occurrence of the symbol, and that will give rise to a spectral modulation. And of course, we have the spectra of the basic pulse, so which is of course standard. There will be a sync waveform that I was showing for the basic pulse. This pulse amplitude modulated signal is can be modeled as a modulated pulse train. The modulation index are the symbols. So we can write xt is equal to k equal to minus infinity to plus infinity, ak p t minus kt. So where ak is the symbols, and because we are, when we estimate the occurrence, usually we take it as independently occurring variables, random variables. So this is discrete random variable. That means the symbols, when it is occurring, there is no correlation between the symbols. Though in actual cases there could be some correlation, but always when we analyze transmission, we assume that they are not correlated. they might be correlated to the source. But when we have coded the source, and so we have kind of decorrelated the information. Then Vt is the basic pulse shape. So which again can be a simple square wave or can be any other. T, capital T, of course, is the symbol duration. That is the duration of 1 bit or duration of 1 bit. Now, if we take one say energet unipolar, polar, or bipolar, you can see that say for energet unipolar, AK will be equal to some level A for symbol 1 and 0 for symbol 0. Say for polar, energet polar, AK equal to A for symbol 1 minus A for symbol 0. Similarly for energet bipolar, AK equal to A minus A alternately for 1, 0 for symbol 0. So Vt is of course most of the cases these are rectangular pulse. We shall see later that we will have some of this to further combat this bandwidth and pulse distortion. So we assume for the time being, let us assume it is a rectangular pulse of unit amplitude. So TB is the duration, therefore we can define say the bit rate or TB equal to 1 by RB or RB equal to 1 by TB. Now because AK we have assumed since the set of AK is or AK is a discrete random process. Since AK is assumed to give a predictability, we assume that this random process is assumed to be of a stationary random process. So stationary random process means its statistics is same with respect to time. So generally you can think of like the simplest kind of statistics for any random process could be the sample mean and the sample variance. Now those are for stationary process. This is independent of time. So that means the statistics or any other statistics. One of the statistics is of course given the generalization of this uh, variance that is known as the autocorrelation. So typically, stationary random process is characterized by average autocorrelation function. Autocorrelation is basically describes the way the signal vary with respect to itself. If we shift the part of the signal and take a projection onto the signal, sum it up, then that brings out the similarity of the signal. Or in other words, the projection could be a simple dot product. If they are numbers, then could be a dot product of the vectors, two vectors. Now, because it is a random, so uh, autocorrelation direct dot product will give the autocorrelations. However, because it's a random process, what we have to do is that we have to take the expectation of the autocorrelation. The autocorrelation function of a random variable A is given by its expectation of the dot product shifted in time. In this case, of course, shifted by number because we are in the discrete domain. So it will be RAN. N is the sample number, is the expectation of AK dot AK minus 1. So if we assume that this discrete random variable is a real one, phase is not involved, so then of course it simply becomes the multiplication of the shifted occurrences. In other words, it could be also the summation of approximated by the summation of the projection of AK onto AK minus 1. So E is the expectation operator. So this summation can be done for case of the stationary random process. Now, in from this autocorrelation is related to the spectrum.
Sir, sir, if we are calculating expectation, there should be some probability involved of source symbols, like maybe AK.
Yes, yes, probability of source symbol will be there. So that if it is it is equiprobable, okay. So then there will be a constant will come here, some constant, okay. Some constant will come. So autocorrelation is related to the spectrum by a popular theorem that is also known as autocorrelation theorem, or by the name of that Wiener Kinchain theorem. As Sxf is equal to 1 by capital T Vf square. N equal to minus infinity to plus infinity. RAN exponential of minus j twice by NF. Capital T. So where Vf is the Fourier transform of the basic pulse. Bt. So basically the two spectrum, there is Vf square is the autocorrelation spectrum of Bt, and this is the autocorrelation spectrum of RAN, the Fourier transform. These two are multiplied. RAN depends on the type of line coding schemes, because as we have defined the AK symbol occurrences are different types, so therefore RN will depend on this line coding scheme. Say for energy at unipolar format, if we assume zero and one are equiprobable, then probability of zero occurrence equal to probability of occurrence of the symbol A, because there is one 0 is occurring, AK is becoming 0 or AK is becoming A. So that is equal to half. So the variance which gives rise to the diffuse spectrum n equal to 0 is expectation of AK square, or AK, in case of complex it would be AK conjugate. So this is equal to 0 into P AK0 plus 1, sorry, A square into P AK equal to A. So this is equal to A square by 2, because this P is probability is half, and for this is for n equal to 0, for AK minus n, for n not equal to 0, there are 4 possible values. Zero, 0, 0, and A square. This is this product. This can be 0, this can be 0. Okay, this can be A, this can be 0, this can be 0, A, and A square. So 3 times 0 multiplied 3 zeros, and 1 time there will be A square. Because AK can take either A or 0. So this multiplication will be 0 into A into A, and A into 0, A into 0 into A. So again, we assume that all these occurrences are assuming that all occurrences are equiprobable. That is, the symbols are statistically independent. The probability of occurrence of the 4 values are 1, 4, or 4 combination are 1, 4. So therefore for n not equal to 0, expectation of AK minus n is equal to 3 zeros of equal probability, 1, 4, plus 1 with A square divided by 4. So that is equal to A square by 4. So RAN equal to S square by 2 for n equal to 0, S square by 4 for n not equal to 0. Then let us write down the spectrum. So then SXF would be that VF is the Fourier transform of that Vt, which is a sinc function. So that is S square, then VF. VF is given by TB S square by 4 into VF, that is TB into, oh sorry, sinc square FTB plus S square by 4 TB sinc square FTB minus infinity to plus infinity. There is a shift is there, so that shift will create a multiplication term with exponential of j twice pi n TB. So this one, this minus infinity to plus infinity, exponential of minus j twice by fn TB equal to 1 by TB train of impulse functions in the time domain, shifted impulse function. Oh no, sorry, train of impulse function in the frequency domain. Therefore, SXF would be S square TB by 4 sinc square FTB, that is the first term, and the second one is S square by 4 delta F. So this is coming from this. I think next day we shall discuss, we will explain this relation further, how it is coming. Thank you.